Hello everybody, and welcome to the latest edition of the Physics Corner, a series of videos in which we show how to set up and solve introductory physics problems. I'm your host, Dr. Christopher Sorolla. Today we're looking at the concept of pressure, specifically water pressure below the surface and air pressure above the surface. Well, what do I mean by that? So, standard air pressure at the surface of the Earth is roughly 100,000 pascals. Now, I know that it's more like 101,000 pascals, but we're going to round off a little bit just for today. And so, that being the air pressure, here's my question. If you're a deep sea diver and you dive down below the water surface, how deep do you have to go to add another half atmosphere's worth of pressure? Or, conversely, suppose you're a mountain climber, how high up a mountain must you go in order to get to half of an atmosphere's total worth of pressure? So we're going in halves of pressures, if you will, like that. Now, because they're two different situations, they're going to require two different formulas. So let's see how that works. We'll do our deep sea diver first. So below the water, it'll look like this. The pressure you'll experience if you are below the water line goes like that. And let me put the knot on there. There we go. This is the pressure due to the atmosphere all by itself, and by definition, the air pressure at the surface of the water is 1 atmosphere, or, again, rounded off, 100,000 pascals. What's this term over here? This term is the contribution of water to the pressure that you feel. So there's the density, there's our friend little g, and here's the depth of the water. Now, the reason physics people use h a lot is h stands for a height or a relative height, but depth is the same basic idea. It's just a matter of going down instead of going up. So if you see physics people do this, that's probably what's going on. There are some places in textbooks which will put a D for depth. That's of course fine too, but let's use H here. So in any case, since we're asking to add an extra half of an atmosphere, we don't need this part here that's already known. This is the piece we need. So if we rewrite it like this, if you prefer, the change in pressure that we're interested in, then the change in pressure due to the depth of the water will be that. All right, so let's go ahead and plug in some numbers. So we already know that we want to achieve half an atmosphere's worth of pressure, and so this number is actually known. So that would be our 50,000 pascals on the left. Over on the right, the density of water is a known idea. That's 1,000 kilograms per cubic meter. We're going to round off G today to 10 meters per second squared. And then the depth, H, is what we're searching for. So we have a problem that looks something like this, which means we need to flip this around, solve for H. So 50,000 pascals, divide by 1,000 kilograms per cubic meter, and 10 meters per second squared. All these are in standard units, and so if you do the math, you'll come up with, 5 meters. Or if you prefer feet, 16 feet. So if you dive below the surface of the water line and you want to, or you're going to feel an extra half of an atmosphere's worth of pressure acting upon you, you will have dived down 16 feet or 5 meters. Separate question, what about going up in the case? Now that's going to be a little bit different. So in the case of the water, we assume, and this is a good assumption for what we're doing, that the water is what we call an incompressible fluid. Which means what? It means the density of the water is the same throughout. Now that's not strictly true, of course. You can imagine that as you go deeper and deeper, very deep into the ocean, the density of water does get a little larger, but not really by that much. It's a very good approximation, especially for shallow dives like this. It's only when you get into several kilometers down that you start to really notice anything happening that way, and people don't just dive down that deep. But the air is different. Air is not incompressible, it's compressible, which means it can change its density very rapidly. What's the change of density like for air? Well, when you're close to the surface, you have all the air's weight upon you, so to speak, and therefore the density and pressure of the air is at its maximum. As you slowly climb up, you're leaving behind a good chunk of that air. The further up you go, the more air you leave behind you. And so the question is, well, how far up do you have to go? Second, because it's not incompressible, that sounds a weird thing to say, it's compressible is how we probably should say that. the density and the pressure of the air simply decrease exponentially as you go upwards. So that's what the second formula is. So above the water, or if you prefer on the mountaintop, our formula now looks like this. And notice it's an exponential formula. Okay, what does that do for us? So a couple of things. This is still our 1 atmosphere, if you will. This is the height above the surface now, and this is a reference height. Now, again, we're going to kind of shave a couple of these things down to manageable sizes, meaning that there are several models of how the atmosphere behaves. We're going to choose a number that is pretty rounded off. So if you see more specific results in different sources, that's probably because they're paying a little bit more attention to very fine details that we're not worried about here. Okay, what we want to do here is give you a sense of how this works, and that's what we'll do. So H naught in this case is 10 kilometers, and what we want to do then is calculate for H. So this, and this are known. This, of course, E is just a number actually, and so we'll need to do a little bit of rearranging algebraic math to figure out what H is. All right, so let's go ahead and set this up. So the atmospheric pressure we want on top of the mountain, or where on the mountain will be, and by the way, that's a giveaway, perhaps, that'll be 1/2 of an atmosphere's worth, or 50,000 pascals if you prefer. It's 1 atmosphere by definition at the level of the water, okay, or again, 100,000 pascals. And then it'll be e to the negative h over, and the number it turns out is 10 kilometers that we're going to use. So again, that's rounded off severely, and it's model dependent, but this is close to what you would get no matter how you approached it, okay? So how do we solve for a system like this? How do we solve it? Well, first of all, let's take care of this part here. So we can just cancel out the atmosphere units, and we have 1/2, right? So we have 1/2 equal to e to the negative h over 10, if you will. Keep it in mind, this will be 10 kilometers for units when we get there. This is a natural exponential, and therefore to undo it, we need a natural logarithm. Now, in a previous episode on sound, we talked about base 10 logarithms and 10 to the power, right? This is the natural logarithm, so we have to use that. So it's e, not 10, and it's ln on your calculator, not log, as it was for that previous particular video. But it's the same kind of idea to undo, if you will, which means I have to do this. To undo this, I need to take the natural log, ln, of 1/2, and the natural log of e to the negative h over 10. Now, when I do natural log of an exponential, those functions undo each other, and that's just simply this fraction then. It's what's ever left behind. Okay. So now, natural log of 1/2, that turns out that will end up giving us a negative number, which will take care of this negative sign here. Let me solve for h then. H is equal to a negative 10 natural log of 1/2. And if we plug in the numbers, natural log of 1/2 is about 0.69, if you will. Take care of the negative signs, they cancel, and we get a 6.9 kilometers. Now, just to say this in units that you might be more familiar with, 6.9 kilometers is also approximately 4.3 miles. So, this is something that comes up for mountain climbers, right? You've probably heard this sort of thing, that the tallest mountain on Earth is close to 5 miles tall, Mount Everest and such, right? And people that climb up to the top of Mount Everest, if you're not in like the best possible shape, and even then it's a dicey proposition, you really need to have some breathing equipment to survive up there for more than a couple of minutes. Why? Because the air is too thin. You're getting less than half of the air that you normally would get to breathe, and it's just not enough to sustain you for any length of real time. And that's also never minding the temperature changes and whatnot. We're just talking about just the simple fact of breathing. But in any case, if you're roughly 4 miles above the surface, or about 7 kilometers above the surface, you're experiencing about half of the air pressure that you would at the waterline. And similarly, again, if you want to dive down below the waterline to add an extra half atmosphere's worth of pressure, you need to dive approximately 5 meters below the surface. Okay. So some different ways to handle pressure of air and water, everybody. Okay, technical support is from Sydney Gautreaux and Sophia Turner, as always. Our sponsors are the University of Mississippi and University of Southern Mississippi. This video is filmed in Hattiesburg, Mississippi. I'm your host, Dr. Christopher Cirola, thanking everybody for your attention, as always, and clear skies.